Ladies and gentlemen, please welcome to the stage from Autodesk, Carl Bass.
Good morning, everyone. Morning. Hey. Okay, so this morning I wanted to talk about capturing reality and designing with reality. And I've spent a lot of my career making things in the computer, digital versions of things that often don't exist yet. You know, when you start with a blank screen and you try to design and engineer something that will eventually exist. But one of the most exciting things for me is all of a sudden this idea of capturing reality. So get rid of that blank screen and start with things that already exist. Because in some ways, despite all the advances over the last 30 or 40 years, only in some realms are we able to create digital models that even approach reality. So we get some of the geometry right, some of the topology right. Sometimes we can make movies and video games that fool our eyes, but it's still not reality. And so I'm really excited about this idea that we can start with reality and then augment it, as you've seen this morning. So let me give you a couple examples of things that I think are interesting and you'll hear more about today. So one is this idea of going out there and being able to capture things like coral reefs. So the idea here is, instead of just having photographs, we can actually have a digital model, if you will, a digital double of what actually exists in the world. And we can watch over time and see how it changes in shape, see how it changes in volume, and really understand the effect. Similarly, you could understand we could do the same thing with icebergs and really understand it. Instead of just anecdotal and photographic information, we can have real-world models, digital versions of the things that exist in the world. And later today, you're going to hear about both of these projects. And there's one project that you're going to hear about later today that I'm super excited about. And this was the capture of the command module from Apollo 11. So this is something that just presented a whole bunch of new, isn't that one incredible? So there's a team from the Smithsonian here, and Brian Matthews is here. They have spent endless hours. I see some other suspects out there that have worked on this thing. I think, is it up to a terabyte of data, something like that? Way more than a terabyte, sub-millimeter accuracy for this. And there were a couple of things that came out of this. First of all, you know, it's kind of interesting. This thing was designed to go to the moon, but when it came back, all of a sudden it became precious. And they put it in the Smithsonian, and for 50 years, nobody touched it. And now, all of a sudden, they were able to go in and begin understanding it. And so this is one of the interesting distinctions, is when we make these digital doubles, all of a sudden we have access in new and interesting ways that may not be possible with the real physical artifact. So in this case, there's a couple of things that they found out. Some of the things that they thought were lost in space were actually still in the module. And they found it when they started to scan it. I think they used like 8 different scanners to try to get this level of resolution. The other thing that was totally cool, what I thought about, is there's actually graffiti on the walls. So probably just having to be in this thing for weeks, the astronauts got bored and, you know, were writing with that pencil or that space pen was too hard. And so they just scrawled on the walls. And so this understanding that you get from actually being able to capture it and examine in greater detail is really, really interesting. Now, one of the things that's happening with everything that's going on with sensing and being able to instrument things to a level is we're not just interested, as you saw, in the geometry and topology of things, but we're able to start understanding how things work. And what's going on is this true democratization in which sensors and data logging and the availability of software to analyze this is coming down to price points that's affordable and accessible by all of us. Software is available to understand it and manipulate it in ways that I think are unimaginable or would have cost millions of dollars only a decade ago. Excuse me. So I would have known what the interaction between this is and all this talk about Internet of Things and sensors and instruments. So about 3 years ago, my son said to me, let's build an electric go-kart. I had no idea why. He had never built anything like it, but he decided that we should build an electric go-kart. And it ended up leading to this interesting thing of capturing reality. So there's Will, and he's welding his go-kart together. This is probably 8 months ago. And here we are down at the Naval Air Station in Alameda, where we took it out. And he's driving it around, and this thing's about 2 inches off the ground and goes about 65 miles an hour. Yeah, we had a couple talks with his mom about, helmets and 5-point harnesses and all the rest. But I mean, look at that thing. This thing flies. And what's interesting in this video is we're capturing it with a drone that's following it. So that's all photographed by the drone. And so my friend who was down there at the time, my friend Chris, who happens to run a drone company, had this idea that said, the drone's going around this way. What if we got rid of the driver and made an autonomous go-kart? And he said, we have all the controls there that already work for the drone. Let's just put it into the go-kart. So we started to do this, and we started to build all of the fixtures and mechanisms to turn the go-kart into an autonomous vehicle. But here's where the story got interesting. So I went to my lathe, and Willie and I were starting to make some parts. And we're making these parts on the lathe, and the lathe, I was across the workshop, and the lathe starts screeching. And it's making this horrible noise that for those who have done metalworking would know is just vibration or chatter, where it's hitting a certain harmonic. And I could tell that we were not only, it sounded bad, we were going to get crappy parts. So I went over to the machine, and I started doing this thing of dialing, turning this knob and dial and feeds and speeds, trying to get the sound to get good so we would get good part quality. And one of the things that was interesting in doing, I started to reach this conclusion that I really didn't know what I was doing. Despite having machined things for 30 years, I'm exploring essentially a multivariate space, and I'm going like this and turning things, and I have no idea if I'm near local minima or maxima, or I'm in a sweet region where almost anything would work, and when I fall off the edge and it starts chattering again, I have no idea which direction to head to get back to where it's good. And so I said, it's interesting though, I can hear this. So what I did is what every reasonable person would do nowadays is I took my cell phone and I put it in a Ziploc bag, and then I taped it to my lathe. And then I ran the lathe and I recorded all the information. And back to this point about democratization, I now have a great data logging tool. It just happens to be my cell phone. Collected all this information. I downloaded this signal processing software, and I started to look for it. I could see exactly where the thing was vibrating. And then I went, and I started to understand what was going on. Then I went one step further, and I realized that that drone actually had even better capabilities than my cell phone. And one of the reasons we are able to have these drones at low cost is because things like GPS and the sensors and the microprocessors have been driven to really cheap levels. So I took the IMU out of my drone, and we put it again in a Ziploc bag and taped it, and then we collected this huge amount of data, and we started to figure out what was going on with the lathe. Now, the end of the story for this is not this one's not quite done yet. But one of the things that we figured out is we could totally understand what was going on, and that was the good part. The bad part is, and I think this is true about all of the information we're collecting, is we still can't close the loop. What I want is, now that I understand what's going on in my lathe, I don't even know why I'm in the middle of this. What I wanted to do is I wanted to figure out what's going on and just tune it to the right feeds and speeds. I shouldn't be involved almost at all. So there's more work to be done on this. But back to the autonomous vehicle. So here's Chris, and this is the first time we do it with a radio control. And here he takes the go-kart, and we've finally built all the mechanisms to hook up to the electric gas and up to the brake and the steering, and there it is driving by itself. And this is all being controlled with the drone software. So then the next thing we said is, okay, let's really do this autonomously. And I'm going to show you this. This is back down at the Naval Air Station. Oops. And by the way, I showed that for a reason. I think it's always interesting, like when people get up on stage, all of these amazing projects, they only show the parts that work. And for anyone who's ever done any of these things, they do, 95% is that, and only 5% is the one that actually works. And just like they have on SportsCenter these days, they used to have the top 10 plays, and now they have the bottom 10 plays. I think when people get up on stage, they should show all the shit that goes wrong, because that's really the experience of all of us who actually build stuff. I think it would be a way more interesting talk to learn from the mistakes than see everything that turns out perfectly. But so that was one of the ones. For those who are curious, it turns out that when you have a magnetometer and a big steel frame, you kind of have to insulate one from the other, or it's really confused about which way was north. It was doing just what it thought it should be doing. Okay, so let me just finish this story and say the go-kart is no longer looks like a taco chip, which is what it looked like after hitting the fence post. It's been straightened out, and it now actually drives by itself. And the amazing thing about that for me is that we actually built this out of less than $100 of electronics. And it essentially does what the first autonomous vehicles did, probably 8-10 years ago. We're at that level for hundreds of dollars, where those projects cost millions of dollars. To finish up the other story is as a result of my experiments with my cell phone and with the IMU of the drone, I actually, someone introduced me to a company who's now building a product, and you can see it in the vise there with the little red and green lights, and it actually changes color based on the sound and on whether or not the tool is sharp. So we're one more step along the way, and you can just look and see tool sharpness, and we're one step away from connecting up to the machine and actually having it control the feeds and speeds. But the thing about all of this democratization of sensors and instrumentation that really makes me excited is this idea of starting to take this information and bring it back into the world that I've lived in of design and engineering. And how do we bring this information back so we can use it to design better things, engineer better things, better understand how the things that we design are used and what would make them better in the future? So we embarked on this interesting project. So we started out with a bunch of guys called the Bandito Brothers. And the Bandito Brothers know how to build and design and drive cars. So we started out, they built this frame, and then they took this frame and they drove it. And they drove it hard. And what was interesting about it is we recorded every force that was exerted on the frame. So we began to understand almost everything about the forces that the frame was subjected to during this arduous drive. And what's interesting about that is oftentimes we have kind of a theoretical or perfect knowledge of what something's going to be exposed to. In this case, we had the actual. And this is where capturing reality gets interesting, because like I said, not just geometric knowledge, not just topological knowledge, but this is actually the forces involved in the performance of this vehicle. And then we took the forces from it, and we put it into this piece of design software, a generative design software that we have called Dreamcatcher. And we put it in there to see if, when it knew the forces it was exposed to, whether we could optimize the design of that chassis to be better. So here it is, and here's the evolution of that into a chassis that's nearly optimal for the forces it would be subjected to. And what was interesting is, rather than talk about any of that geometry, we specified the outcomes that we wanted. And that's the important part of the generative software, is that the computer is going through thousands and thousands of iterations, testing them digitally to come up with a near optimal result. And so it's this interesting combination of incredible cleverness and incredible brute force to get there. And so this is one of them. But, now what's interesting about it, too, to me is it looks somewhat biological. And many of the shapes that come out of this are somewhat biological. And there's certainly a parallel to how animals and people have evolved, and that we go through this evolution, and we find this thing, we find a near optimal shape, but it happens over millions of years. This is something that you're doing on the Amazon cloud, and you're hoping to do it in minutes or hours, not over generations and millennia. So here's the result of that. Here's one of the results that was made for fabrication, and one of the inputs was what material. And this one is actually the chromoly one that it was designed for, and here's another version of it that was done for titanium. So again, you can talk about the outcome you want, and as long as you can digitally simulate it, we can use it as one of the inputs to the design. And so it's really important to be able to capture not only the performance criteria, but things such as the manufacturability of it as well. So here you can watch it going through some of these iterations. And so this is the computer designing it without human intervention. And I think this is, incredible. And when you go back to where I started this talk, which is the idea that I've been involved in people starting really at the lowest level, drawing lines and rectangles and circles and trying to build things from the ground up to get to interesting things like the airplanes and the cars that are all around us. I think this is one of the great leaps, that comes from the ability to have what people might label AI or machine intelligence and machine learning, where we're able to digitally simulate and produce nearly optimal things just by relying on the fact that we can use vast amounts of computer time. And what we talk to the computer about is the results we want, rather than how to go about designing it. And rather than that process that, kind of plagues the world of engineering today of doing iteration after iteration, we're now enabling a level of abstraction and communication with the computer in the world of design and engineering that we've never seen before. Thank you.